You were probably starting to wonder when we might tell you what's happening tonight. Come at 6:30, it starts at 6:30, it starts at 6:30, and you all came right at 6:30, thank you so much. Give yourselves a hand. So my name is Amy Stewart McIntosh. I'm the executive director at Kutandara, the studio where we do this thing. That I can hardly tell who that whoop was because it sounded so much like me. That was my daughter. We're so happy to be partnering with Neve Kodesh tonight on this Big Round Mama inaugural event. It's Earth Day. Let's say Happy Earth! Happy Earth Day. Thanks for coming tonight to help bring hope and community and a sense of we're not alone in this. So thanks for being here. So what you just heard was marimba music from Zimbabwe. I know, Jacqueline turned me down and now I'm like, now I have to shout. I just like hearing my own voice. So that was marimba music from Zimbabwe, played on these beautiful wooden instruments, marimbas. And before that, if you were here really early, you heard David Simon and I playing these, what Westerners might call thumb pianos, in that fiberglass bowl. That's Imbira Zabadzimu in Adeze, and that's also music from the Shona people of Zimbabwe. We wanted to use this music tonight to bring people together. We've been doing this music in Boulder County for 26 years, and we brought lots of folks together, and we're so excited to be able to do the work of spreading Zimbabwean music to the world because it's healing and it brings people together, and that's what the world needs right now. Yeah. So I'm married to this fabulous guy. He's amazing. When my mom was alive, she used to say he looked like my grandfather. Why wouldn't he shave that beard? Because it's part of him now. That's that guy right over there. Let's give it up for Randy McIntosh, who some months ago had a dream. And I'm going to ask him to come and tell about his dream and how this idea of bringing people together with this music came to be. And then he's going to introduce our speaker for the night, which is the next thing on the agenda. But after the speaker is done, we're going to have a little Q&A or discussion or dialogue, but don't go right when that's done because we have one more marimba group, and they came here at 4 o'clock to set up, and they've been waiting to play, so I hope you'll stay and listen to our last group. Our first group was Chiroto, which means dreams. Let's hear it for them. Wave your hand, Chiroto. Say that with me. And they've only been playing together a very short time. This was their first official public performance. And they do great. And then the group that you heard after that, in the purple, that was Chapungu, which means eagle. Eagles. Raise your hands. That was them. Give them a hand. Chapungu. They've been together a really long time, and I've been so blessed to be able to work with them for a number of years. So thank you, Chapungu. And then what you're waiting for later is Tanaka, our senior teen ensemble. So Don't go away. Here's Randy McIntosh, our artistic director, to tell you about how he came up with this idea, the vision for Big Round Mama.
Let's hear it for Amy Stewart McIntosh, the director of us all. And thank you for telling me what I'm doing up here, Amy. But Chiroto, the first group that played, it's their first performance. That's my class. Amy's been teaching them for 4 weeks, and wow, you guys have come so far. I'm so proud of you. While you were playing, one of the people sitting next to me looked at me and said, "Do you ever look at the adults and just go, oh, they're so cute?"
Yes.
And I was doing that. Thank you for being here, Chiroto, and also Chapungu. So, Becky, how long have you been playing? 1 year longer than my daughter
Is alive.
is alive. So that must mean 12. If you stick around, my daughter will tell you how old she is, because she's in the band Tanaka. Now she's worried that I don't know how old she is. So she was born in 2007, so 17, right? Mm-hmm. Okay, so
I had a dream.
I have a dream. I had a dream. I feel like Martin Luther King, but my dream was actually while I was asleep. And these instruments are from Zimbabwe, and in Zimbabwe, I've been taught many times, listen to your dreams. Listen. Your ancestors are trying to speak to you through your dreams. And that's a different dream than I learned growing up, the American dream of you can pursue your dream if you just pick up your bootstraps and work hard every day and don't give up. You can live the American dream. I'm learning more to listen, and I think that's why we are here. My dream was very much you guys, friends, family, students, getting together, and you know, it was a dream, so it's not clear exactly what we were doing, but it was for the environment, and maybe some of it was for a protest, and maybe some of it was for the planting of trees. But the main theme was all of the problems that we're having with this global crisis stems from the fact that we've forgotten how to be in community.
Woo!
Yeah.
That's the 17-year-old who
Yeah.
and rolling her eyes at me. So, you know, like, that's why we're here. And may this be the first of many of getting together, playing music to get together and have fun. That's what these instruments are for. And fun in Zimbabwe isn't just, woo, fun. It's doing something with purpose. And that's what makes it fun. So let's continue on. Is Chris coming up now? Is that what's happening next? Okay, well, I was given this paper of all sorts of dope stuff that this guy does. Come on up, Chris. I'm not even going to, Christopher, I'm not going to try to say your last name, but you can tell us all these cool things that you do.
I didn't give that to you.
Okay.
You better read it.
Susan gave it to me and was hoping I'd say something, but I'm dyslexic, so I don't want to screw it up. But thank you for being here. Come on.
Want me to read it?
And while he's getting ready, I just want to take a second to thank 3 rock stars, David Simon, Emily Warm, and Susan Kodish, who took the
first of all, thanks for inviting me here, and I didn't realize I was the manifestation of your dream. You're really putting the bar high.
You weren't naked.
What's that?
You weren't naked, thank goodness.
I think I'm glad I didn't. All right. Well, I'll just introduce myself for a second, and then I'll talk to you about climate. Those are my kids. It's just the background on my. It's not part of the slides, but those are my kids, and I do know how old they are. They're 10 and 12. Dina's on the right side. He's my 12-year-old boy. My daughter CJ is on the left-hand side there. But it's a great background. So.
Where's the photo?
We're in Santa Barbara, just going for a walk. Yeah, really spring break last year, I think. So yeah, I'm Chris Tarnauskas. I'm a professor at the University of Colorado Boulder in the Atmospheric and Oceanic Sciences Department. Thank you. Everything that's
Yes.
okay. You can just move this.
The acoustics are weird in this.
Yeah, sure. I was going to try to be loud enough, but this will be helpful. Losing my voice lately. Okay. Right there in your face. Let's go with this. So I was invited sort of out of nowhere. This is the first time I've heard marimba music, which I very much enjoyed, and thank you very much. Closer, is this better? Okay, great.
But I'm also a techie.
We'll put her right here.
I'm gonna like make it right for your height.
Perfect.
Because you're a tall guy. Here, everything you're gonna say.
And yeah, when I was told about this event by Susan Kodish, I thought I've given a lot of outreach talks about climate change in my career, and I think the next time I give an outreach talk about climate change or a lecture at CU, I'm really going to wish that it was sort of bookended by uplifting music like this. I hate to say it, but I don't have great news for you tonight. But wouldn't it be nice to be like a traveling road show?
Yes.
Every time I go give a lecture at CU, can you just come and like
Yes.
set them up?
Yes.
And I'll knock them down. Great. Yeah, I'll knock them down, and then at the end you can bring
Lift them up.
That'd be really good. So I have no idea. I had no idea about this event or what you're all interested in, but I'm going to talk about climate change, and I want to invite you from the very get-go, honestly, to interrupt me with questions. You don't have to wait for the end. I'm a visual learner, so a lot of the stuff I'm going to show you is sort of graphical, graphs, visualizations. And I don't think there's any equations in this talk, so that's nice, right? But interrupt me at any point, okay, please. And if there's something that I'm talking about that doesn't make any sense, it's probably not just you, okay? Probably everybody around you is wondering the same thing. So just stop me and we'll talk about it. And I don't care if I don't get through all of my slides. What's more important is that we just talk about climate change. I share some knowledge and information that you might find interesting, and we can have a conversation. Hopefully a nice hearty Q&A at the end. Okay, so there's a little cut off, but it's okay. It's climate change, how we imagine it. So let's start by talking about greenhouse gases. A lot of smart people in this room. So greenhouse gases have been measured by NOAA, the National Oceanic and Atmospheric Administration, since about 1958. Can anybody in this room please identify a greenhouse gas? Can anybody name one of the greenhouse gases? Methane! Methane, that's a good one. That's not the first one that most people bring up, but it's, you know what, it's the most powerful greenhouse gas of them all, so good for you. HFCs, did I hear somebody say carbon dioxide as well? Okay, so yeah, methane, if you didn't know, it's about 25 times more powerful or potent as a greenhouse gas than carbon dioxide. But why do you think we tend to worry about carbon dioxide, or you hear about it a lot more? Why do you think that is? What's that? Yeah, cars, like we emit a lot of that. CO2 is about 200 times as abundant as methane. And also, when we emit carbon dioxide into the atmosphere, unlike methane, it's there for thousands of years. It takes a long time to come out of the atmosphere. Methane, it's gone in about 3 years if we emit it, but we keep emitting it. So there's not just one greenhouse gas. I just wanted to throw that out there. But we've been measuring these this is the Mauna Loa Observatory on top of Mauna Loa in Hawaii, and we measure greenhouse gases there because they're far away. This is far away from most of the sources of them. So we're kind of getting a pristine global atmosphere perspective. You don't want to just measure it right next to a factory. We want to really get a sense of like what's the concentration of this stuff in the global atmosphere. So here's a graph, one of so many graphs you're going to see tonight. But I've cleverly hidden the numbers on the y-axis of the graph over here. I suppose you can see my cursor. Okay, so I hid the numbers. So you knew about different greenhouse gases, you know about why we worry about CO2, for example. Can anybody in here guess, or do you just know, the current, roughly, the current concentration of carbon dioxide in the global atmosphere? Okay, by the way, we usually express these while you're thinking. We usually express these in terms of parts per million. That's how, I'm not a chemist, I hate chemistry, but the atmospheric chemists, they express this in parts per million. So it's like if you've got 1 million little cubes of air, how many, and that represents the whole global atmosphere. How many of those cubes would you say is filled up with carbon dioxide?
350.
Oh, you're all so close. You're probably thinking a couple decades ago though, because right now, so those are the numbers over there. So this is like, I don't know, when you think about global warming, this is just that one number like every climate scientist on the planet has memorized. We know how much carbon dioxide there is in the atmosphere. 425 parts per million this past year. And so you can kind of see, I don't know, it's kind of fun, or depressing, however you want to look at it. Think about when you were born. I don't know. You don't have to tell anybody if you were born on the left-hand side. It's all right. Think about when your kids were born. I don't know. How much the carbon dioxide was then, and think about how much it rose since then, and just kind of look at the unwavering trend in this line, right? It's just tiny little undulations along the way, but like think back to COVID, right? We all heard probably that we emitted a little bit less carbon dioxide in 2020 and 2021, right? But where's that? I mean, that doesn't show up here, right? So one thing I want you to, before I inundate you with even more graphs, one thing I want you to think about is the distinction between emissions and concentration. This is concentration. This is how much of the stuff is presently in the atmosphere. Emissions is how much additional are we putting in year to year. So it's like a bank account, right? The balance is the concentration. Your deposits each year, those are the emissions. So just because we emitted a little bit less in the middle of a global pandemic doesn't mean we emitted zero or we took any out. It still actually went, it still goes up over time. Okay, so that's carbon dioxide. Bonus round. Okay, so Venus, it's a picture of Venus. The surface temperature of Venus is a whopping 465 degrees Celsius, or 870 degrees Fahrenheit. It's a little bit closer to the sun, but that's not why it's that hot. It's that hot mostly because there's a little bit more carbon dioxide in Venus's atmosphere. So can anybody take a guess as to how, so think back to the earthly number was 425 parts per million, right? So take a guess as to how many parts per million, what's the concentration of carbon dioxide in Venus's atmosphere?
300,000. 1,500.
You're both really close. It's almost 1 million. Very good. Give yourselves a round of applause. You were reasonably close. You were reasonably close. Close to all million parts per million. It's right. It's like 96%, 96.5% carbon dioxide. Things have gotten a little out of control on Venus, right? That's probably why we're going to send Katy Perry to Mars and not Venus. But in all seriousness, I'm going to show you, these are 3 of the most important graphs in my view. You already know one of them. It's the one on the lower right-hand side. But these are like the most important 3 graphs that sort of tell the story of how climate change has been progressing over the past several decades, and sort of what are these key numbers. So remember, I mentioned there's emissions and there's concentration. So the graph up here, and I apologize, it isn't coming through as sharp as I would have liked, but these are actual emissions of carbon dioxide expressed in gigatons of carbon, but don't worry about all that. It's just the anthropogenic input of carbon year after year. And so if you kind of look at the very end of the graph, it says right here, we as a global civilization emitted about 10.2 of these gigatons of carbon in the year 2024. But you can actually see a few notable events like COVID, global financial crisis, dissolution of the Soviet Union, and so on. So we do actually have, sometimes very unfortunate means of, but we do have control over our emissions. If we really want to change the equation, emissions is how to do it, and we've done it in the past, even if it was on accident in this case. And this is the growth rate of carbon dioxide. So it just looks like another graph going up, but what it is by how much is the CO2 in the atmosphere increasing each year, okay? So what it says, the way you would kind of read it is say, all right, this last bar here from the year 2024, it says it's about 3.3, okay? So this graph over here, the actual CO2 in the atmosphere went up by 3.3 parts per million in 2024. So these are just really iconic numbers and graphs that show the evolution of our contribution to the carbon dioxide in the atmosphere. Like I said, if you have any questions along the way, please don't hesitate to interrupt me. So let's take a look. Yeah, please.
It seems to me that there are so many more emitters now than in 1960. Do you expect more of an exponential rise?
Well, I've got a slide that I can show. I'm glad you asked that, and I think I'm glad that I buried this in my extra slides, because if you actually look country by country, which I know I have here, here we go. So this is the same thing. You're looking at the emissions over time, but now it's broken down by country. And it's actually kind of interesting. You can see that there are countries and regions of the world where it's already flatlined. So for example, I know these are hard to read, so I'll point some of them out. The black line, let's go with this one. This is the USA. And you can see there was kind of an inflection point maybe around the year 2004, 2005, something like that, where believe it or not, our emissions have actually been declining. I wish the far left was showing, it's not zero. We're not even close to zero or anything like that, but it's declining. And I think that's really interesting and notable. Same thing with the EU, which is the blue line here, probably a few decades before us. The US, the European Union's emissions started declining. If you do that on a per capita basis, you can kind of see the same thing. But this is China, and China around 2000, maybe around the time that the USA started to decline in terms of emissions, China's emissions have been really skyrocketing. And so this is a lot of, same with India, although it's a lower overall level. So places that haven't had their industrial revolution like the US are having it now in a really big way, in a pretty advanced way. So we're having, good question, but I think it's just the devil's in the details of like breaking it down by sector and by country and things like that.
Quick follow-up question.
Yeah, please.
So for China and India, do we know how much their increase relates or correlates to increased standard of living in their country, or how much of it is because they're producing things and shipping on pallets?
Yeah, there are more. There's a project called the Global Carbon Project. If you want that level of sort of breakdown, go to globalcarbonbudget.org or something like that. And they have these kinds of graphs that break it down by sector and all kinds of things. You can sort of get a little first pass insight on the answer to your question by looking at per capita. You can sort of think of that as a sort of quality of life type of indicator. And the USA is still the highest emitter on a per capita basis. Where's China? China would be this one here. So that's on the rise. This is on the rise as well. So yeah, I mean, it's not just a story of booming population, you know, it's also per capita, and that comes with wealth. It's well correlated with GDP, so. All right, so I do want to take a much longer term view because, I'm so sorry.
Oh,
Yeah.
actually, if you're going to do longer term, I guess that's what my question is.
Yeah, if I don't get to you, if I don't answer what you're wondering, let me know, okay?
Yeah.
And so let's take a little trip down to Antarctica. And Antarctica is an interesting place for climate scientists because it's a place that records climate evolution over very long periods of time. And the way that works is that in the Antarctic ice sheet, where every year there's another layer laid down of ice on top of Antarctica, each year that new layer of ice forms, it traps air bubbles in that ice. And it actually stays there pretty well. These air bubbles stay in the ice, and so we can just go down there, as if it's that easy, but we can go down there, and we can drill into the Antarctic ice sheet, and what you kind of see is, it's as you would expect, the youngest or newest layers are on top, and the further down you drill, the further back in time you're going. So it's like a time capsule. So we can actually extract these cores. We call this an ice core. They're very, very long. We preserve them, and we can very carefully extract the little air bubbles, the air from the bubbles that are locked in the ice. We can use radiocarbon dating methods and all sorts of techniques to put a timeline to that as well. So we can actually use this to reconstruct how things like carbon dioxide or methane or dust concentration went up and down over a really long period of time, like almost 1 million years, which is a useful perspective considering how long we've been around. So to show you what that looks like, this little graph in the lower left-hand side shows you that. So just to orient you with the time scale here, this 800, which you can't read, I'm sure, unless you're in the front row and still have good eyes, but that says 800, and that's 800,000 years ago. So that's almost 1 million years ago. And then it goes forward to the present, right about there where it says 0, that's kind of like getting closer to today. Okay, and so what you can see is this up and down between maybe 200, remember that 425 that we're at today? So it kind of bounces up and down between about 200 and 300 parts per million over time. Those are the ice age cycles. We know why this happens. This is some combination of, you know how the Earth is tilted, and that's how we have seasons, and right now it's tilted about 23.5 degrees, but it's not always 23.5 degrees. It actually wobbles back and forth over these like hundreds of thousands of years. And there's some other stuff too, with the geometry of the Earth and Sun that changes perfectly naturally over really long time scales. And that sets up this ice age cycling that we've gone in and out of over the last 1 million years, which you can see very clearly here. But I want to show you, and just kind of think about an ice age in your head, right? Like it looks nothing like it is out there right now. Like the Laurentide ice sheet came down all the way to Iowa. The whole world was a very different place. Think about how dramatic that is. And all that took was about a 100 part per million CO2 change between the depth of an ice age and a warm period in between. So where are we today on that graph? So from the end of the reconstruction of the CO2 from the ice cores, go forward to 1960, which is about when we started carefully measuring CO2 on top of Mauna Loa in Hawaii. So that bumps us up to about 317 in 1960. And then 2024, as I told you, it was 425 parts per million. So just look at that. And I think to me, it's always kind of, even though I've been studying this stuff for a long time, it never sort of fails to amaze me how this indicator of global climate, the concentration of a greenhouse gas in the atmosphere, which is bounced around like this, and look where we've taken it now. It almost just looks like a perfectly vertical line, but I assure you, it's really a graph.
Can I ask a question?
Yeah, please.
This feels like a stupid question.
No, there's no such thing. It's all good.
How can you be sure, and I'm just like a little devil's advocate because I'm
Fine.
sure you're sure, like how can you be sure that the CO2 levels in the ice cores are what cause the glacial cycles?
Oh yeah, it's actually very complicated. It's not just that
Okay.
those changed.
I was like,
Yeah, no.
okay.
That's a really good, in fact, it's climate scientists that have worked out the details of
Okay.
that. It's not like a hidden secret or anything
Okay.
like that. There's something called feedbacks in the climate system. So if you start warming things a little bit going in one direction, you kind of change things like the photosynthesis of the land surface, the respiration of marine life, and then that's going to start to get the carbon cycle changing in a big way. So it's not like one is really in the driver's seat versus
Gotcha.
the other on these timescales.
Okay.
But on our human timescales, that is definitely a cause, and like absolutely no doubt from a physics perspective that when we add greenhouse gases to the atmosphere, for very well understood reasons, we do expect the atmosphere to warm.
Yes.
And I can talk about that here
Great.
too. I have some slides on that because I think it's useful for everybody to know this stuff, even if you're, and I appreciate the sort of devil's advocate sort of questioning because
Well-
you know what, you're gonna run into people who ask you the same
Well, and I
question.
just wanted you to connect the dots.
Yes, exactly. Okay, so yeah, it always just amazes me that this is now so far outside the range of what's happened in the past. And then if you want to think about like, okay, well, what's happened over that period of time? We all know that the surface of the Earth is warming. We've mapped this out. We've measured this. At least so far, NASA and NOAA have been able to do this. I don't mean to laugh, but it's not clear that this will continue, but that's probably another story. So we know what has happened in response to that increase in CO2 from 317 to 425. We know the surface of the Earth is warmed, and we know exactly how that works. It's the greenhouse. Going into the future, though, there's a lot of interest in predicting the future climate because people have to be prepared for it. All of the sectors, from agriculture, you can't find a sector in the global economy that's not at least somehow related to the environment. Okay, so predicting the future of the climate, this is important not just for people who live right on the coast and are worried about sea level, but this is important for a lot of reasons. So we have to sort of come up with future predictions first of how much carbon dioxide there's going to be in the atmosphere. And we can't just have one, sort of one prediction, like, okay, by year 2100, it's going to be X amount. That's not really helpful. We certainly don't know how society is going to evolve technologically and in terms of emissions and population. There's a lot of variables. So we have to come up with some kind of a range of possible scenarios of CO2 from now until the end of the century. And one of them is this right here. And this is sort of the lower of them. This is called RCP 4.5. It doesn't matter all the little details, but one model would predict that we're going to have 540 parts per million CO2 in the atmosphere by 2100. Another scenario that is sort of used to help offer predictions of climate in the future is 625. And then the one that we sort of coin business as usual, or burn baby burn, or whatever you want to call it, is this one here, which gets us to 930 parts per million of CO2 by the end of the century. And just take a look at that graph. Like, I'm not making up these numbers. These are carbon dioxide concentrations by the end of the century that very large teams, interdisciplinary teams of economists, technology, experts, population scholars have all come together and said, okay, this is sort of the range of possible CO2 concentrations in the future. And it's just kind of an outlandish number. Yeah, it's a question. So I'm, one of the themes that I was asked to talk about is health, human health. So I'm actually that's right where I'm gonna go next in terms of CO2. Most of the time, we think of, that's a great question. If you've ever seen like Apollo 13, have you seen Apollo 13? And there's like you may not remember this scene, but it's like when everything's kind of going sideways, the thing that they're tracking is the CO2. They're really worried about the CO2 buildup in that capsule that they're in. There's well-known cognitive impacts on human cognitive impacts when the CO2 does get really high. We would be walking around okay with the, we probably wouldn't notice it outside, with like fresh air and things like this, but what this would do is cause a really high level of global warming, and then all of the impacts of global warming from sea level rise, melting ice sheets and glaciers, and then everything that stems from there would be a problem. I would personally be more worried about heat waves. Like if I'm worried about my health and CO2 is about 1,000 parts per million, I'm gonna be able to breathe that air, but that's gonna be a world where it's gonna be a lot warmer than it is right now. And so that's gonna shift things around a little bit. Okay. Since I'm just doing nothing but jumping around anyways, so let's go to what how temperature has changed and how some of the other symptoms have changed. And is somebody going to keep me honest on time? Because
I'm going to you have 10 more minutes to kind of like wrap it up, and
Great.
then 10 minutes of questions.
Okay, let's do that. Great. So let me just show you some of the immediate impacts of this rise in CO2 that we're already able to see. So this is the up-to-date kind of classic global warming graph. This represents all my numbers on the left side are gone, so I can tell you it's anything. I can assure you that right up here at the top, what it says is 1.5 degrees Celsius higher than the past. So anyways, this is the global average temperature since 1880. This is compiled by NASA. These are from direct measurements of surface temperature over the planet. Absolutely no doubt it's been going up. And it's, the trend is far beyond the uncertainty. So we know all that, but let's look at a couple other interesting things. So we have as a scientist who studies this unfortunate problem, one nice thing is that it's a really interesting time to study it because we have amazing technology. So we have this satellite system called GRACE, and it stands for Gravity, Recovery, and Climate Experiment. And the reason it's called that is that there's these two satellites, not just one, and this is kind of an artist's rendition, as you can tell, but there are two satellites that both orbit the Earth. One follows the other, okay? Bear with me here. So there's a really, high, really expensive laser that's being pointed between the two of them, and that laser, it measures the distance between the two satellites. That's kind of the whole thing, all right? So you've got these two satellites. One is chasing the other around the Earth. So what happens when these satellites approach something really big, like a mountain or the Greenland ice sheet or Antarctica? The leading one accelerates, right? Because everybody knows that gravity pulls things towards you, right? So the leading satellite goes forward, it lurches forward a little bit, and of course that laser senses that. It knows just how much farther apart it's gotten. But then eventually, the trailing satellite catches up, because of course it's going to go over the same mountain, it's going to go over the same Greenland ice sheet. And so we launched this satellite back in the early 2000s, or this system of satellites. And we did it in order to measure things like the Greenland ice sheet. Just based on that tiny little difference in distance between the two satellites, you go over the Greenland ice sheet enough times from outer space, you can actually back out the mass of the Greenland ice sheet and then track it over time. You can imagine Greenland is really big. No one wants to go there and just kind of count how many chunks of ice there are. Like, this is the best way to measure it. And so we've been doing that since the early 2000s. And I'm going to show you the graph of it. This is why you're going to need more marimba music pretty
Yes.
soon, I can
Yes.
assure you.
Yes.
Greenland's on the left, all right? So when I hit play, what you're going to see is it's going to map out, like it's going to be red, wherever we have rapid losses of ice. And then the graph here is going to show you where we are in time in terms of this change. So again, sorry, it's hard to read, but it's like 2000, 2004, 2005. And so this is showing the change in the mass of the Greenland ice sheet. The units are gigatons, but it's, you know, it's a mass. And it shows it going down. And unfortunately, it shows that where we're losing mass from Greenland is not in the middle, where maybe it would just like refreeze or something like that. We're losing it around the edges, and then it's just flowing out into the ocean. If you look really carefully, you can kind of see the lines showing you that. So you can see how much mass is being lost, and it's nobody really relates to gigatons, not even me. So let's think about how much mass this is. This little, if you're wondering, we lost the satellite, and it took us that amount of time to launch the next one. You can guess it wasn't a, well,
It wasn't a big day.
interesting time too. But anyway, I'll leave
So
that.
they can really get that much spatial resolution out of the satellite?
Yeah, because it goes over a different part of it every time. So this is a polar orbiting satellite. In other words, it just goes from pole to pole over and over, but the Earth is spinning underneath it. So you're able to really map it out like this is like an X-ray, you know, it's really cool. Yeah.
You talk a little bit about the albedo.
Yeah, what is there to say about albedo? Albedo, what it's defined as like how reflective is a surface, all right? So ice has a high albedo, it reflects a lot of sunlight back to space. This change in albedo, for example, is kind of why we're seeing so much warming near the pole. So if we go back to this, if you look at the map of observed temperature change, you notice there's a lot more warming at high latitudes. Some of this is because once you lose ice, and unfortunately the polar region is kind of covered up, but imagine the Arctic Ocean, right? There's no land there. It's not like Antarctica where there's a continent. You've got ocean, right? But it's covered in sea ice. If you melt that, what does the ocean look like compared to ice? It's darker, right? So now, you know, like if you're wearing a black shirt on a sunny day, you feel hotter. So that's kind of like what's happening to the ocean surface there. Now it's absorbing more heat. And is that kind of some of the things you were thinking about with? Yeah. But just back to Greenland for a second. I won't have too much time to talk about health, but you all have great questions. Back to Greenland, because nobody really relates to gigatons. So how much does this mean? So in 1 year, in which year was this actually? Okay, from 2014. This is just a little infographic from NASA, but I love the calculation that they do. In 2014, we lost 303 gigatons of ice from the Greenland ice sheet. How much water did that add to our ocean? So it turns out, and I got to look carefully to read this, an Olympic-sized swimming pool, okay, it could stretch to the moon and back 16 times. That's how much water that is that we lost from Greenland in 1 year, which is kind of hard to imagine, but that's the volume of water. So these are huge amounts of water. This is tied in, as you can imagine, with other environmental issues and climate change impacts like sea level rise. Where do you think this water is going? It's going into the ocean, and the sea level rises for two reasons. One is that it heats up. So as you know, when things heat up, they expand, right? That's about half of it. This is something you can impress your friends with. If somebody asks you, why is sea level rising? You can tell them it's about half because the water is expanding and half because we're adding water, such as from Greenland, Antarctica, and glaciers. And so I guess I should probably bring it to a close because in true professor fashion, I've sort of rambled on, but you all had wonderful questions. You know, thinking about I guess in the spirit of this event and it's Earth Day and everything, like, you ask yourself, who is the patient here? There's going to be health impacts of climate change. I can just sort of comment on a couple of them without going into any detail on them, even though yeah. So one of the things that I study in my lab is actually vector-borne diseases. Have you heard of malaria and Zika and dengue? I mean, these are all essentially tied to mosquitoes. And mosquitoes breed when it's wet. Temperature has an impact and things like that. So this is one of the things that I study. That's one of the more probably complicated ones and harder to actually work out the dynamics, but just think about extreme heat, hurricanes getting stronger. If there are more fires, there's more air pollution, allergens, in other parts of the world especially, and in the Southwest here, there's going to be some important impacts on the water supply. Yeah. So, you know, who's the patient here? And is it, you know, is it us? Is it the planet? I don't know where this came from, but I love the phrase, there's no healthy people on a sick planet. And of course, if someone's sick, you want to think about, like, how do we make this better? And so I just want to, my last slide here, I think, before opening up to questions is, you know, back to the CO2 emissions. This is what's behind it all. CO2 emissions, they've been going up. And so we can actually sort of do some quick back of the envelope calculations and figure out what are we going to have to do now in order to avoid and then any threshold you want. Like, do you remember the Paris Climate Agreement? Kind of sounds like a thing of the past now. The idea was to avoid 2 degrees of global warming. Everyone sort of said, okay, 1.5 isn't good, 2's not good. Let's avoid 2 though. Let's not go past that. And so we can do a calculation today. This is the emissions today, all the way up to now. And then in order to avoid 2 degrees of global warming, this has to be our emissions for the next several years. It has to, like, by 5 o'clock tomorrow, we have to start dropping these emissions. And there's no positive way to put this. I'm really sorry, but, like, this is actually the state. But think about, like, COVID in the beginning when people were talking about bending the curve, right? The earlier you start, the easier it's going to be to follow a sort of a sane pathway down to safety, right? So, you know, 2 degrees, this is what it has to look like. If we want to avoid 1.5 degrees of global warming, which we're almost there right now. By some metrics, we've already surpassed that. Our emissions have to go down to 0, like, by the end of the 2030s, you know, from these really high levels of emissions that we're at now. But had we started back in, let's say, 2010, okay, this could have been our emissions future in order to keep us at the 2 degrees. And look at how much easier, I mean, it wouldn't have been easy, but look at how much easier that would have been than starting today. And unfortunately, possibly some number of years from now, I'll be giving the same talk and this will be the line that we're jealous of. We wish we had started here and started to drop them at that rate in order to avoid 2 degrees of global warming. All right, we need some music. So just to summarize my points here, which hopefully were interesting and thought-provoking and motivating perhaps. Our emissions, concentration, and growth rate, they're record highs since we've been measuring them. This is new territory for the modern human species. We know what CO2 was like over the past almost million years. This is well beyond that. I tried to find a way to write this. Given historical emissions, hope of meeting the Paris Agreement target of 2 degrees requires thrilling levels of optimism. Sorry. And yeah, there's going to be health impacts that are going to be difficult to deal with, especially if we can't continue measuring things the way we are today. But It comes back to the emissions. The best way to mitigate the problem is to aggressively reduce the emissions starting now. So please, more questions, and I don't know how we are on time. But you
I have a question.
Yeah.
Have you watched the Netflix special about Bill Gates?
I don't think so.
Okay, so there's this great, I think it's great, special 4-part miniseries on Bill Gates and what he's doing, and one of the 4 episodes is about the climate crisis, and what he details in that, and you know, he's throwing a lot of money at a lot of things to try to do a lot of good things, and
Yeah.
one of the things that he details in that episode is that it's really hard for any one individual or one family or one community to have a meaningful impact because the bulk of CO2 emissions are coming from sectors that we don't really have that much control over, like manufacturing and agriculture. And so is like, if you had anything like a
Yeah.
charge to give us, you know, the 50 of us in the room tonight, like, where do you find your hope?
I hate that question. because
Sorry.
I mean that in a nice way.
Yeah, of
It's a
course.
very good question, but the way you set that up is spot on. This is, you know, you could look at some time in the past where like remembering to turn the light off really could have made a difference. And I want to believe, you know, I do believe that like every drop in the bucket counts, you know, like I'm not that cynical. But you're right, these are the emissions that we know are coming, are behind the climate change signals that were recorded with unprecedented fidelity, with no uncertainty about where it's coming from. These are coming from very large scale forces in motion in the world. And so, yeah, I mean, I love it when my colleagues are like, I'm taking the train to the meeting instead of flying like across the country. And it's like, and I admire this, I try to do my part too, but then it's like, are the big emitters worrying about the same thing? And I don't know. I mean, the obvious answer to me is think carefully about how you vote, because that's probably going to be the highest leverage at this point in 2025. This was a long time ago that like all the little individual level actions could counteract something that large. I just think about like thinking carefully about how you're going to vote and how that's going to have what the implications are for your vote for these environmental issues that you care about.
Thanks.
Yeah.
So there are some swing for the fences technologies out there. People talk about carbon reclamation, but the energy required is probably too high. But then there are things like solar shades.
Yeah.
You know,
Yeah.
I mean, are you tracking any of those? And are there any
Oh, yeah.
that excite you?
Yeah, I mean, so you're talking about geoengineering. That's kind of the scientist's term, that category for everything you just said is geoengineering. So in general, just to back up for a sec, if I may, when we talk about how to address climate change or how to solve the problem, things generally fall into one of two camps. There's mitigation, which is like reduce the cause of it in the first place, like reduce the CO2 emissions, that's mitigation. And then there's geoengineering, which different flavors of them have very different sort of philosophical and ethical profiles, right? So for example, you brought up carbon scrubbing, carbon sequestration. Gosh, if we had a way to, at scale, pull the carbon dioxide right out of the atmosphere, I'd have a hard time complaining about that. I mean, we would get to continue whatever way of life we want, as long as we can pull the carbon dioxide out. It's not actually feasible at the moment, but like that would be a swing for the fences thing, especially if you can just at power plants where a lot of carbon dioxide is being emitted or in a tailpipe. If we could actually just stop it from getting in the atmosphere, what's the harm? There's no inherent harm in what, right? But there's other approaches like, okay, what if we could stop so much sunlight from getting to the earth and cool things back down? It's a little bit of a different calculation, isn't it? Because we're saying Well, we can keep emitting our carbon dioxide and not worry about it because we're going to counteract it by keeping it cool. The second we lose, and there's a couple ways to doing that. There's like literally bazillions of, we could put bazillions of space mirrors in orbit that would just reflect just enough, 5% of the solar radiation. Okay, or we can inject aerosols in the stratosphere, the next level up, you know, kind of just above where the airplanes fly. Aerosols, stratospheric aerosols, they would reflect a little bit of sunlight too. That's got its own issues, but the minute we lose the political will to keep these cooling mechanisms in place, because we've just kind of given ourselves a free pass to continue to up our CO2s, who cares? Also, there's other things that, it's not just the warming. Think about the ocean. If you've ever heard of ocean acidification. So the more CO2 we put in the atmosphere, the more is absorbed by the ocean. In fact, the ocean has absorbed about half of the CO2 already that we've emitted. All those curves that I've shown you with like big rises in CO2, it'd be twice as high if it wasn't for the ocean. This is harming marine life. So that would be a loser in that geoengineering solution, because we wouldn't be able to stop it from going into the ocean. And there's other strategies too, but yeah, I mean, I sure wouldn't complain at this point if we found a way to get the CO2 out of the atmosphere. Then I don't have to feel quite as bad about what I'm emitting, and it cannot have a downstream effect if we've removed it. I'm pretty worried about the knock-on effects we don't know about with like space mirrors and stratospheric aerosols. That's going to change rainfall patterns. We model that, we simulate it. Some countries like lose their seasonal rains when we change the global energy balance like that. I mean, this is like a minefield. But it always comes up for good reason. We need it, right? It's looking like that point. Yeah.
Very simple question.
You sure?
What can we do?
Yeah, I know. Right? Didn't I just say no? Like I
Vote.
said.
In the olden days, like you said, about the lights, you know, and make sure that we were
Because I think it's also dangerous to go to despair and think that there's nothing you can do. And I think making real tiny contributions
Yeah.
that may or may not impact the big picture.
Yeah, every little difference. You know, I sort of come back to this. This was COVID.
Yeah.
You know what I mean?
Yeah.
And think about how much that, like, of course, that was nobody's intended way to solve the climate crisis, obviously, right? But the whole world came to a halt. Like, that was a huge change for a while, and that's all that happened to the emissions. But remember, the emissions are just a deposit to the account. If you go to 2020 or 2021 on this graph, I can't even see a flinch in it. So this is going in this direction until there's like really large-scale political will to make this happen. And the Paris Climate Agreement looked pretty good. There was a lot of, you know, every few years there's a, you know, so a positive story would be the Kyoto Protocol. So do you remember the CFCs, right, that were ruining the ozone? Honest scientists had been measuring the ozone hole. We knew exactly what was causing it. We came together and banned CFCs. And we watched the ozone hole recover. It was beautiful. And it was all from the Kyoto Protocol. So we can do that. I mean, that's a really big change. We deserve some credit for that. But that was, you know, that required people to be told it's illegal to have that refrigerator with those CFCs in it. It wasn't, you know, it was a very large-scale policy where there was political will, and then it just became the new norm with that technology. So maybe the things that emit CO2 are replaced over time in the way that they were forced to be with the Kyoto Protocol for CFCs. Yeah, the question back here.
On electric vehicles, if you rent an apartment, you're not going to have a place to plug it in unless you go to a charging station. I think about 60% of Boulder residents are renters, and there's the mining of the lithium, cobalt, nickel, copper has a devastating effect on the environment. It's a double-edged sword, and lithium and cobalt, much of it is mined in the Congo, which has a terrible effect on the environment, and the people get paid close to nothing with no protective equipment and hardly any tools, and then up the supply chain, millions are made.
Yes, I hear you. It is a double-edged sword. The energy has to come from somewhere. It's, yeah, I mean, we emit less. We, on average, I think it's been proven that, and quantified like rigorously, that electric vehicles, even when you account for other things, end up contributing less CO2 emissions. But it's not nothing, because kind of like you alluded to, the energy does still have to come from somewhere for the batteries, including the production. Yeah, a couple more questions over here.
Are these materials still available on the federal sites?
For now.
Okay.
I mean, I'm not even joking. We're rapidly downloading critical data sets right now. It's, yeah, it's weird.
I mean, to not even be able to share this information with people.
I probably have a cease and desist already from this talk. No, I'm just kidding.
Yeah. But that's what's most scary right now.
Yeah, I mean, yeah. Not even being able to quantify a problem sure makes it hard to communicate it and solve it.
Right. If you had outreach from other, I guess I'm hearing a lot of other countries are trying to grab our climate experts right now.
Yeah.
So you've seen that?
Yeah.
Yeah.
I'm glad I know French. Let's just put it that way. No, I love my job at CU. I don't want to go anywhere. And your hand was as well. Sorry.
Yeah, let's just take one more.
Okay, sure.
In a short way,
Yeah.
you haven't mentioned nuclear.
I'm sorry, what was that?
You haven't said anything about nuclear energy.
Which is something I'll
I'm
be honest with you, I
not in
don't.
agreement because I'm old enough to go, oh, that's really scary.
Yeah.
But China's ahead
Yeah.
in what they're building.
Yeah, I'll be perfectly honest, it's just not something that I know a lot about. And so I do it's not because to me it's politically dicey or anything like that. I just don't know that much about it. I'm not an engineer, and I'm sure you know just as much about nuclear as me.
Abby?
I'm wondering if there's much research happening around what the benefit would be of us all eating less meat.
There's tons of
In
research.
terms of what we do, we all eat 3 times a day. And it seems like it could have a significant impact.
Yeah, actually, I'm with you there. These graphs that kind of break it down by country, I don't think I have it by sector, but it's a surprisingly large contributor of CO2 emissions is from meat. And it's, not just like the cows and the methane and the joke there, but it's like the whole industry, which surprises me. And it's not something I know that much about, but I've seen the data on the same sort of graphs where it would compare it on apples to apples with other sectors and industries, and it's there. It's really funny. Yeah, I mean that's certainly something that individual choice would have to be what drives that. I'm sure. I can imagine a pretty tough battle of legislating this, but that's certainly something that
I mean, at some point we're going to have to give up some of our comfort. And so I just want to put that in the field.
I think it's a great point.
There are a number of people who are eating vegan in this room, so if you want to come talk to us, raise your hands, vegans. Come talk to us about that. A lot of us made that choice because of the environment. So let's give Chris a warm thank you. And if you want to be informed about
about upcoming Big Mama conversations. We're going to include breakout groups next time because it sounds like lots of folks want to visit and talk, and we didn't think of that. So there should have been a registration when you came in. If we don't have your email, just make sure we have it on your way out. Another round of applause for Chris. Thank you so much, Chris. One of the reasons that we wanted to use Zimbabwe music to bring you together around this conversation was that many of us have felt that Zimbabwe music is so healing. And so, like Chris said, we need some more marimba music to end the night. And you've been waiting for our senior band, Tanaka. They're going to play for about half an hour. Feel free to dance, feel free to mingle, feel free to exchange contact information. I know that Emily bought some seltzers, so there's some drinks at the back there. And again, a huge thank you and sense of gratitude for Neve Kodesh for partnering with us on this and opening a space to us.
Okay. Hi guys. We, as Amy said, are Tanaka and we are the senior performance marimba band at Kutanda. So, like Amy said, if you guys are feeling the music, and you should be, get up and dance and enjoy it because the energy that you give us, we give back. If you're at all interested in doing this kind of thing, go talk to Amy. We have plenty of programs for adults and children. Sit back there.
We hope you guys are having fun. I'm just going to take a quick second to introduce everyone in the band. So starting off with our bass, we have Ellen. On baritone, we have Evie. Then on tenors, we have Jude, Aurora, Lola. And on sopranos, we have Eliza and Dave. And then, yeah, I'm Ollie. We hope you enjoy the next song.
have such an important discussion and play amazing music. Special thanks to Amy for organizing this for us. And to Randy for showing us this amazing music. I hope you guys enjoy. One, two, 1, 2, 3, 4.